Question 13. Here we've got a given exponential model. Let's go ahead and put that into our calculator. We're going to do some computations with it. So in the calculator, y1 equals 235 times, in parentheses, 612 divided by 235 raised to, in parentheses, t divided by 4. X divided by 4 on the calculator. So there's the model. You should recognize this as a two-point exponential form. We can see that on this model, the initial value is 235. It's a growth model because at t equal 4, the output will be 612. That's the second point. We've got the initial value and the value a of 4. So it's the two-point exponential form. Part A, let's calculate a of 4. Well, we just got it. You can see that if you plug 4 in there, you're going to get 612 from the two-point exponential form. If you don't see that, you can answer this anyway. You just go quit out of here and plug 4 into the model. Plug 4 in by calculating y1 of 4 on the calculator. And there it is, 612. Part B, solve the equation a of t equals 1,000. Okay, so we've got the model already stored in y1. We'll put the other side of the equation into y2. So 1,000 is our target. We know that's going to happen after 4 units. Let's look at an every 5-unit table. So under table set, 0 for start, 5 for change, and run the table function, second table. And if we look down that list, we can see that we're going to be at 1,000 within 10 units. So let's graph this on the interval from 0 to 10. X min 0, X max 10, run zoom fit, and we should see that intersection point. There's the model increasing at an increasing rate, like all increasing exponential models do. And there's the intersection point. Calc, intersect, enter, 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 and the intersection point is about 6.05. T equals 6.05. Part C. Find the average rate of change, delta A over delta T, on the intervals 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10. So those are interconnected intervals that are splitting up the interval from 0 to 10, which is actually what we've graphed. We've got the graph of our function on the interval from 0 to 10 right now. So let's, we could do all of these average rates of change individually. Like the average rate of change on the interval from 0 to 2 would be a of 2 minus a of 0 all over 2 minus 0. We could do all of them that way. It's just, this would be easier to do using the spreadsheet capability of our calculator. So I'm going to do it that way. Stat, edit, and I'm going to put all of the input values that are involved in those interconnected intervals, 0, 2, 4, 6, 8, and 10. And then I want the output values for each of those inputs. I'm looking for the points on the curve with those inputs. So let's go up to L2 and calculate y1. That's where the model's stored, of L1. So it'll plug all of the inputs into the model and get those outputs. It's not part of the procedure of getting the average rates of change right now, but I can go to the to y equals, turn plot 1 on. While I'm here, I'm going to get rid of that 1000, which I'm no longer using. So with plot 1 turned on and the model on, I can go back to that graph, which is on the interval from 0 to 10, and I can see the points that have been plotted. The average rates of change are the slopes between neighboring points. Like the average rate of change on the interval from 0 to 2 would be the slope of the line connecting this point and that point. And so on. We can see that those average rates of change are going to be increasing. They're getting steeper. Those slopes are getting steeper. That's also another way of saying we're increasing at an increasing rate here. So let's get those average rates of change. We're going to move over to L3, point up to it, and do delta list L2 divided by delta list L1. Change in outputs, which are in L2, divided by change in inputs, which are in L1. So there are average rates of change. The average rate of change of the function a of t on the interval from 0 to 2 is 72.12. On the interval from 2 to 4 is 116.38. On the interval from 4 to 6, it's 187.81. On the interval from 6 to 8, it's 303.09. On the interval from 8 to 10, the last one, 489. .12. That interval, on the interval from 0 to 2, the 72.12, I interpret that as on that 2-unit interval, on average, the amounts are increasing by 72.12 y units per x unit. That's the way you interpret an average rate of change. It's a slope. And so on. So increasing average rates of change here as we move from left to right on the graph. Let's go to part D. Find the growth rate of this function as a percent. Okay, the model, let's go right here. That model can be rewritten like this. A of t equals 235 times 612 over 235. That exponent is 1/4 times x. I can take the 1/4 power first and then take the x power. The t power. I'm writing a of t, so t on paper. So that is a different form of the same model, and that's the standard form of an exponential curve. This number right here is the base b, the growth factor. This is a sub 0 times b to the t power. So we have the base of the exponential function, and that means the growth rate, r, is equal to that base, 612 over 235 to the 1/4, and then minus 1. On an exponential curve, r is equal to base minus 1. And so let's calculate that. 612 divided by 235 raised to the 1/4 and then minus 1. There's the growth rate as a pure decimal. Multiply by 100 to convert it to a percent, and it's equal to 27 0.03%. There's the growth rate.